Hello, and I would like to thank the organizers for the opportunity to speak today. I'm going to present the joint work with Oliver Euler and Jalal Shatta from the Courant Institute. And this work is essentially about the kinetic theory of systems that preserve quadratic sign-definite invariant, the energy, alongside a sign-indefinite invariant. So you can have in mind, for example, helicity. It just needs to be quadratic. And so this is a feature shared by many dispersive systems in geophysics. And this is mainly due to the special structure of the Euler equation. And to my feeling, many times in kinetical studies, sign-indefinite invariants do not get a lot of attention because they're not cascaded in the classical sense. So today I want to show you that they actually have beautiful consequences in the theoretical description. So they really simplify the kinetic theory, and they allowed us to find an exact solution of the kinetic equation, which we believe to be practically relevant. And they also practically change or affect the direction of the cascade, of the energy cascade. So dispersive waves in geophysical systems, they owe their existence to some combination of gravity, rotation, and curvature of the Earth. So of course the rotation in this simulation is in the wrong direction. So let me reverse time, and then we will get it in the right direction. Okay, and today as a study case, I will focus on internal gravity waves. And internal gravity waves, they appear, for example, in the ocean due to gravity that stratifies the density of water. And they're non-trivial already in the linear level. So for those who are working on inertial waves, they're very familiar with that because they behave very similarly. So if you write the dispersion relation in spherical coordinates, you will see that it's scale independent, and it's given as the cosine of the angle between the horizontal plane and the vertical direction. And for those who are less familiar with internal gravity waves, so let me show you a demonstration, a small experiment. So this is a long wave tank. It has two layers of fluids. The blue one represents the deep water, which are denser and heavier, and the upper one represents the warm water in the ocean. There's a handle that will create tides, and an obstacle which represent topography in the ocean bottom. And you will see that once he starts rocking the handle, so an internal wave will propagate between the two layers. And just notice that there are no surface waves, so there are really internal waves, and that's also why they're called internal gravity waves. So they're especially important case for theoretical studies because a significant percentage of them are far too small in scale to be resolved numerically, and they believed to have an important impact on climate change processes, for example. And so if climate models, resolution good climate models are about 10 to 20 kilometers, so most of the mixing due to internal gravity waves is occurring on scales which are lower than that. So they're really important for theoretical study. So mathematically, if you ask yourself, how do you find waves or how waves are created inside an incompressible fluid? So the answer is the breakdown of rotational invariance. So this is the two-dimensional Boussinesq equation, and David wrote the same equation just for temperature difference. So z will be the vertical direction, and x will be one of the horizontal directions. And this equation describes two-dimensional internal waves on a vertical plane. And it's obtained, you can obtain it from the Euler equation if you assume a linear density in the profile, and then you consider deviations and you write the equation for the deviations. So psi here is the stream function, so I write it in for the vorticity. So the Laplacian of psi is minus of the vorticity. And eta, it's called the vertical displacement. If you're more comfortable thinking about buoyancy, it's just the minus n squared buoyancy, where n is the buoyancy frequency. And n, the buoyancy frequency, you can think about this as gravity over the mean density. And for those who are working on inertial waves, so this equation, for example, looks like a rotating fluid with the constant rate n. So this equation has two parts. One is really looks like the Euler equation with density continuity, and it's isotropic and nonlinear. And the other part is the linear skew-symmetric part that is there due to gravity, and the part that breaks the rotational invariance of the Euler equation. And this is also the part that produces waves. And it's not hard to check that these equations, they conserve a quadratic energy, which is the sum of the kinetic energy plus the potential energy. And they also conserve another quadratic invariant. It's called the pseudo-momentum. You can think about this as the correlation between the vorticity and the buoyancy field. And if it's easier for you, you can have in mind helicity or entropy. Mathematically, their origin is the same. So clearly, I'm not interested in trying to look for the behavior or understand the behavior of a specific solution, but rather in the statistics of solutions. And like many other dispersive partial differential equations, if you insert energy at some localized compact region, and then you dissipate at very distinct scale, so and you look at the energy, the spectral energy density, then it exhibits some power law. And so this is the averaged over angle. So this system is not isotropic, but if you average it over angles and you look at the spectrum, it clearly has some power law, and we would like to compute this power law. And so these are preliminary results of direct numerical simulations joined with Vincent Lavelle. And it's important to say that these, so a priori, when we did this work, it was not even clear to us that we will have this power law. And we finished this work much earlier before we started looking at direct numerical simulations, and we're glad to say that our theoretical prediction actually works. And you might be surprised that this is an open problem. It was not solved yet, but it's a hard problem with a long history, and probably the first one who tried to solve it was Hasselmann in the 60s, and there were many important classical works since then. Maybe the reason it was not solved yet is because, okay, we will all agree that the turbulence is a hard problem, and probably non-isotropic turbulence is harder, but here, because we have dispersive waves, so we can think about dispersive waves if they have small amplitudes and they have, on one hand, a bounded region where they do not disperse completely, but on the other hand, they have enough space, so they're not packed. So we can think about them as weakly interacting particles if their amplitudes are small, and then we can try and write kinetic theory, like the Boltzmann equation, and then we will, in theory, have a closed equation. It will be nonlinear, but it will be closed for the energy density. And so kinetic theory for dispersive waves is usually called wave turbulence. And the first attempt to use wave turbulent approach to study internal gravity waves in 3 dimensions was 20 years ago. And there were important and beautiful works, but at the bottom line, as of now, there are no relevant predictions for the energy spectrum that was observed. And the reason for that, I think it's the combination of 2 factors. So first, experimentally, it's very hard to observe wave turbulence in stratified fluids in the lab, because there are additional structures that tend to occupy prominent part of the energy. So one of them is, they're called shear and vertical modes. The vertical modes and the shear modes, and they are similar to geostrophic mode, for example, for rotating turbulence, and they all correspond to modes with 0 frequency. So in order to observe them and to observe wave turbulence in stratified fluid in experiment, you need to remove shear modes. And the other reason might be theoretical, and it's the kinetic equation in 3 dimensions is very complicated, and I think that here for 2D comes one of the contributions of our work. So we were able to derive a kinetic equation in 2 dimensions, which is much more simpler because we used the pseudo-momentum, which really simplifies the kinetic equation. So I think that 2 dimensions is not just a theoretical exercise. I think it can be relevant for the lab, and I hope that this demonstration of the long tank, so if you can imagine a much longer tank, then I think that 2D will be relevant for experiments. And I think that it can also be relevant in the ocean. So this is a simulation. So I think that 2-dimensional vertical slice in the ocean will be relevant in the neighborhood of 1-dimensional topographic structures, like the Hawaiian Ridge. So if I have 1-dimensional chain of mountains, then at least locally, I can convince at least myself that if I take a vertical slice, then the 2-dimensional Boussinesq equation should apply there because I have symmetry along the chain of mountains. And if you ask yourself, how does wave turbulence look like? So you take this Boussinesq equation and you run a simulation or you run an experiment, so you can have many regimes. So you can have strong turbulence, you can have some regime in between, and if you ask yourself how does wave turbulence looks like, so this is a snapshot of the vorticity. This is from direct numerical simulations again, so this is a snapshot of vorticity. So you see it's a turbulent flow, but it's really different than strong turbulence, and the vorticity is stratified. And the real test is to take the spatiotemporal spectrum, so you take the energy, you Fourier transform it in time, and you want to see that most of the energy is indeed concentrated along the linear dispersion relations. So most of the energy is contained in waves, and then you can be sure that you're in wave turbulence regime. Okay, so if I want to write a kinetic equation for 2-dimensional Boussinesq, so conceptually it's very similar to the Boltzmann equation, and Grisha talked about this a little bit yesterday, but I would like to remind you some basics of the Boltzmann equation derivation, because the derivation for dispersive waves conceptually is very similar. So you start with n particles with given position and velocity. Their free dynamics is given by these equations, and we assume that the collisions are elastic. So if V1 collides with V2, and the outgoing particles are V1 prime and V12, so we have momentum conservation and energy conservation. And if we consider hard sphere particles with diameter epsilon, so that the kinetic description will give us a density function, which depends on n and epsilon, and it is the number of particles at time t with velocity v at location x contained in the region q. And in the Boltzmann grad limit, so if we take n to infinity, epsilon the diameter to 0, and we do that in a particular rate such that n times epsilon squared is going to a constant, the solutions, the density function will converge to a solution of the Boltzmann equation. So this is the Boltzmann equation, which you're probably familiar with. So it has a free transport part. If space is homogeneous, you don't have this operator. And there is a collision term on the right-hand side. So it looks pretty complicated. So how to read this complicated equation? It has, we're not surprised, it has the momentum conservation, a delta that gives us, keeps the momentum conserved, another delta function that gives mass conservation, and it has a collision part. So it has a gain term, particles that collide and give us particles with velocity v, and the last terms, the particles with velocity v that lost their velocity, and this is why they're the last term. So if we want to try and write a kinetic equation for partial differential equation, dispersive partial differential equation. So if the partial differential equation is canonical, like Grisha presented yesterday, then it's clear who are the particles. You write your Hamiltonian in canonical variables. These are your particles, and then you go and expand, assuming interaction is weak, and you get a kinetic equation. And indeed, classical wave turbulence was mostly developed for canonical Hamiltonian and isotropic systems. And it's not surprising that if you ask ChatGPT which variable should I use in order to write the kinetic equation of internal gravity waves, it would answer only canonical. well, good luck with that, because the Boussinesq equation, so it's not isotropic, and it's clearly not a canonical Hamiltonian system. And it's clearer if you would write it in a variational form. So the energy would be the Hamiltonian, it's quadratic, and I will write it as the equations as a variational principle using, so I combine the variables and I group them in one variable, then I can write the variation of the energy with respect to this variable. And then if I had a canonical Hamiltonian system, then I will have here a skew-symmetric form. If it's canonical, I can bring it to the canonical form, which is invertible, and that's why we have a canonical representation. But clearly, because the energy is quadratic, and we know that the equations of motion are quadratic, so if I want to write it in terms of a skew-symmetric form, this form has to be linear in the dynamical variable, and it will also make it a degenerate form. So it has a non-trivial kernel, and that clearly shows us that it's a non-canonical Hamiltonian system. And one reason why it's useful to write it in this form is first that now it's clear that the origin of the invariance is clearer. So it's clear that energy is indeed the conserved charge with respect to translation in time, because it's really the Hamiltonian. And the origin of the second invariant, the pseudo-momentum, is a little bit more interesting. So it's called the Casimir of the Poisson form. So the Poisson form, it was just a generalization in the 70s of Hamiltonian symplectic structures in order to include the class of Euler-Arnold equations, and in particular the Euler equation. So it's called the Casimir. It's conserved because it's in the kernel of this Poisson form, and the same is true for helicity, for example, and entropy also in Euler equation, and entropy also in Rossby-Case equation. They all have the same mathematical structure. So now if I want to write a kinetic equation, there is the possibility of trying to bring this equation to a canonical Hamiltonian form and I can do that with fixing a gauge, but in general this is a very hard procedure, and it was done, for example, for Rossby waves by Zakharov, but we will not go this path, and we will consider much more natural variables. That will be the natural variables with respect to the pseudo-momentum. So we will consider the equations on a torus of size L. And the reason I want to be on a torus is because at this stage I don't want to account for boundary conditions, and I want also to control the rate at which I will eventually take L to infinity, but I want to control the volume in which the dispersive waves are interacting, because I don't want them to disperse away. And so the natural variables with respect to the pseudo-momentum, they're almost the Fourier transform of the fields. They're a little bit different, but essentially they correspond to waves that are going left or right in the horizontal direction. They can still propagate in all the vertical directions, and they split the pseudo-momentum into positive part and negative part. So right-going waves will have positive pseudo-momentum, and left-going waves will have negative pseudo-momentum, and they diagonalize the pseudo-momentum. And maybe one important thing for this workshop, that if I write it as a density in the wave amplitudes, then it has this coefficient here, which is given essentially by the amplitude of the wave number, and this may play a role with making the energy cascade going backwards, which I will talk about at the end. Okay, so these variables, they also diagonalize the energy, so they make our lives much easier when we try to write a kinetic equation. And the representation of these equations in this form was already done in the 80s, but with a different context. And one thing that is important to remember is because these variables diagonalize the energy and the pseudo-momentum, and these are two exactly conserved quantities, so they yield constraints on the interaction coefficient. Okay, so now I would like to write the kinetic equation, and I will just do that schematically because the procedure is really similar to the Boltzmann equation. So I will consider waves here there because the nonlinearity is quadratic, then the waves are interacting in particles rather than in pairs or four particles like in the Boltzmann equation, and I will take the kinetic limit. So I will take v to 0, the interaction of the dispersive waves, I will take it to 0. So this corresponds to taking the diameter to 0 of the particles, and I will consider an infinite regime. So that corresponds to n going to infinity in the Boltzmann equation. And the most interesting part is that if I will consider long times, because I'm really interested in a steady state, then I will get energy conservation. And the energy conservation with respect to dispersive waves is a little bit more interesting. So in long times, partial differential equations are dominated by pseudo resonances, and resonances are interaction. So if I'm in a three-wave system, a resonant interaction is such that the sum of the frequencies is 0 of the interacting waves. So those that will give me the most contributions to the kinetic equation will be those that are almost 0. If they are 0 exactly, they actually pose a problem, and this is the most of the work in deriving a kinetic equation is in approximating them. So if you will take time to infinity, you will see that the interactions, the dominant interactions are concentrating along the resonant manifold with this rate in time. Okay, so we write a kinetic equation. It has a similar structure to the Boltzmann equation. It has a collision integral. Because we assume that space is homogeneous, I don't have a transport term. And so it's nonlinear in the energy density, but it's closed. And the sum over, so we were on a torus and we had a sum over discrete waves. So once I took L to infinity and time to infinity, then I have here integration over a continuous space. But I'm integrating only over the resonant manifold, so only on resonant interactions, and I still have momentum conservation. So this is the analogy with the Boltzmann equation. And so it might look like a bit scary equation, but you get used to it. And it can actually be very simplified using the pseudo momentum. Okay, so I will just say that quickly. If you remember, then we have the constraints coming from energy conservation and pseudo momentum conservation, and you can think about it. So for every triad alpha, beta, gamma, you can think about them as vectors in 3 dimensions, and then you actually get that they must be orthogonal to two other vectors. So the vector of coefficients must be orthogonal to the vector 1, 1, 1, and also the vectors of the coefficients coming from the pseudo momentum conservation. And then if you consider these constraints on the resonant manifold, you will get that the vector of frequencies must point in the same direction as the vector of interaction coefficients. And so they're pointing in the same direction, so they are proportional by some factor, and that really simplifies the kinetic equation, because now we can write it in terms of one interaction coefficient and the frequencies. And it might not look much simpler, but you can really appreciate the simplification if you try to look for solutions of the original equation with respect to this much more friendlier version. Even numerically, it's a nightmare, so it's a real simplification. And before we use this simplification to find a solution, so let me just point out that, so this dispersion relation with, as opposed to, for example, isotropic systems, they vanish on a pretty large set. So these frequencies vanish on the axis of the entire axis of kz, or when kx is equal to 0, and that really poses a problem. But I remind you that these are actually correspond to shear modes that I said that in order to observe wave turbulence, at least in the lab, they need to be removed. So we're fine with that. We just need to remember that our equation does not hold in this vicinity. Okay, so we're going to use the simplified version of the kinetic equation in order to find steady solutions. And I will just note that there are known solutions for anisotropic kinetic equations that were derived in the 70s. And they use an approximation. So if you go into this approximation when one of the wave numbers is much smaller than the other, so all the functions become B-homogeneous in Kx and Kz. And then you can look for B-homogeneous solutions. And they were found, for example, in the three-dimensional case, but most of them are probably not relevant. They give a collision, a diverging collision integral, and they were never been observed. The same goes for Rossby waves. So we will use a slightly different approach. So we will not take any approximation. We will treat the exact equations, the exact kinetic equation. And if you write the interaction coefficient and the frequency in polar coordinates, so you will see that they're not isotropic, but they are symmetric with respect to dilation, or they're homogeneous in scale. So you can look for solutions which are also symmetric with respect to dilation, and that would fix this homogeneous form, which is also separable. So you will have one part which is scale invariant with some power law, and another angular part. So if we will indeed find such a solution, it tells you something about how a cascade can proceed in non-isotropic systems. So it will still be scale invariant in scale, but it will have some distribution in angles. And I will just note that there is such solution, a trivial solution to these equations. So if you take W0 and this function to be 1 or proportional to a variable which we call the temperature, and you plug it in the kinetic equation, so you just get here a sum of the frequencies, and on the resonant manifold these vanish, and this is an exact solution. So to find a non-trivial solution, we take this form and we substitute it in the kinetic equation, and then we get that the collision integral separates to one part which is homogeneous, and it has some power which is given by the homogeneity degree of the interaction coefficients in the frequency, and one part which is angular. And we look for solutions that give this part, this collision integral, that make it 0. So we're actually looking for a part that will make this collision integral, the angular part, into 0, and we need to fix the power of the radial part. And we actually expect a curve of solution, so we expect that for every power W, we will have an angular part, which will make the angular part of the collision integral to 0. And along this curve, we will have that the derivative with respect to this variable W will make this function into 0. And now there's a question is how can I pick up a solution, the relevant solution along this curve W? So, so this becomes a problem of assigning relevant boundary conditions to the steady kinetic equation. And because energy is conserved, I can write the kinetic equation formally in terms of a two-dimensional flux. And in more than one dimension, this flux is not well defined. It's not surprising. So if I consider a particular solution, I can have many fluxes that correspond to the same solution because I have gauge freedom. So I can change my flux with a rotor of any stream function. It will give me the same solution. But on the other hand, if I fix a relevant flux, that would choose a unique solution. So I need to fix the boundary condition to get a solution. And then if I'm going to think which are the relevant boundary conditions, so if I'm assuming the case that I inject energy in a compact domain, and I'm going to look for the solution far away from the energy insertion point, then I'm expecting to see the flux, the radial flux going to 0. And in particular, this product is, if I want it to be 0, so okay, so if I'm going to see
So I'm expecting at infinity to see only a radial flux without any angular fluxes. So then I can write the divergence of the flux part just in terms of a radial flux. And I want to have a zero divergent flux, and I also expect it to go to zero when it goes to infinity. So that fixes that this product has to be only a function of theta. And then if I integrate this equation in K, so I just get this simple product. And now it's clear that if I want this product to be only a function of theta, I need to choose the special value W equals to W naught. And okay, and for the two-dimensional Boussinesq equation, we found this value, it's -3. And then because when I take W to W naught, it will make this denominator divergent, then the flux will actually be given as a derivative in W of the angular part. So it's really the special solution, the only special solution that will give me a non-zero flux. All the other fluxes, because this is zero, will give me a zero flux, all the other W's. And we also find another solution. It's an approximate solution. When I consider waves only propagating to the right or to the left, it's not important. It's just that I want the pseudo-momentum to concentrate on one of the branches. So I will consider a case when I only have right-going propagating waves horizontally. They can still propagate in all directions in 2 dimensions. And then we find a slightly different power, which represents pseudo-momentum flux, and it's given by -3.5. So if you wonder what is this power, so it's not a magical power, it's just the homogeneity degree of the interaction coefficient plus the space dimensionality. So if we're in 3 dimensions, we expect for the energy cascade to have -4. Okay, so now if we want to look so we have one part, it's of the energy spectrum, it's -3, k to the -3, and I want to look for the angular part. And I'm going to plug it back in the kinetic equation and look for the angular part. And if I consider forcing or boundary condition, which is symmetric with respect to the axis, so it does not need to be isotropic, just symmetric with respect to the axis, then I expect to have a solution which is symmetric with respect to the axis. And I have a good candidate for that because of how the collision integral looks like. And this is my candidate. And when I thought about, when I realized that this is a good candidate, so I took it, I plugged it in the collision integral, and it gave me a diverging collision integral. And then my first response was, okay, it's irrelevant, it's not local as we call it in wave turbulence, so I need to look for another solution. And then I went home at night and I gave it a second thought, and then I thought to myself, actually it's not a diverging solution, it's actually a solution where my collision integral on one end is going to -infinity, and at the other end it's going to +infinity. So maybe formally, exactly at this point, it's going to 0. I just need to regularize my function. So if I add, for example, a little imaginary part, I can regularize it. And then I asked myself, so what would be the relevant regularizer? And I was speaking in my head with my PhD advisor. He was yelling at me at my head and said it's completely nonsense, and why would you do that? But I decided to try that anyway. And then I thought, I remembered that my equations should not be actually valid on this entire curve. So actually maybe I need to regularize exactly around this curve, and that will give me a meaningful solution. So what I do is that I take away an angular section of width delta around pi/2, which is exactly where the dispersion relation are going to 0 and where my equations should not hold. And so I introduce this regulator, and now I'm going to try to take delta to 0 and pray that it will work. And indeed, when we try the limiting procedure and we take delta to 0, we get that this is a solution, a meaningful solution of the kinetic equation. So this is how it looks in the wave number domain, two-dimensional domain. So it proceeds as -3. The angular dependence is cosine to the -2. And for us, it was very exciting to find this solution because it looks different than the classical known solutions. And we also believe that it's relevant for experiments or direct numerical simulation. We think that you can observe it. And we find this solution in two distinct cases. So one case is when the pseudo momentum is 0 on average. So I have on average the same amount of right-going and left-going propagating waves horizontally. And it's also an approximate solution in the case when the pseudo momentum is concentrated on one of the branches. So for example, the positive branch. And if you ask yourself, so this is something, so I added the slide yesterday after Grisha's talk. So if you would ask yourself, what is the message of this diverging collision integral? So it actually has two important messages. So first is the clear, transparent message that your theory fails on this line when the dispersion relation goes to 0. And if you want to write a full theory that includes shear modes, so we have some ideas towards that, then you need to change your degrees of freedom. So they will not be right-going and left-going waves. They will be something else if you want also to include shear modes. But we're fine with this case if we want to be relevant for experiments where actually shear modes are removed. And the other thing is that actually if you add rotation, which is what is happening, for example, in the ocean, then that fixes the problem of the dispersion relation, because then you have a small regulator and the dispersion relation does not go to 0, and you have this gap, which is the frequency of the rotation of the Earth. Okay, and now let us go back to the energy flux the energy flux of this solution. So we will find the energy flux also in a limiting procedure, and we get that the energy flux as a function of the angle over the total flux is converging to sinus theta, and this is also what we expected. We expected that most of the energy will be transferred along modes that have small frequency, and less energy is transferred around and with respect to direction where the frequency is higher. So this is maybe the most relevant part for this workshop. So if we consider the approximate solution where most of the pseudo momentum is concentrated on one of the branches, so it's mostly positive definite. So maybe it's not surprising, because if you remember, the ratio between the densities of energy and pseudo momentum is given by a monotonic function. So if you look at the energy flux in the approximate solution, so it gives you a negative flux. And on one hand, it's not surprising, but on the other hand, I'm not aware of a derivation of a flux and an exact flux for anisotropic solutions. And in general, for an anisotropic system, the flux can do weird things. So it's not necessarily has to go for all angles backwards in scale, but it does for the approximate solution. And there is the question that is remaining is how relevant is this solution for long times for the Boussinesq equation. If it is relevant for long times, then it's actually very exciting, because we would be able to see an inverse energy cascade and internal gravity waves, which was not ever observed yet. Okay, so I will finish here and I'll conclude. So we derived for the first time the two-dimensional equation for internal gravity waves. And we were heavily using the fact that it has a second quadratic invariant, a pseudo momentum. It allowed us to simplify to write the kinetic equation, because we found the variables with respect to pseudo momentum. It allowed us to simplify the kinetic equation and get a much friendlier version. And this simplification was making the search for a steady state solution also much more easier. And we obtained a solution by fixing boundary conditions. And we're very optimistic regarding this solution. We think it's relevant for experiments or direct numerical simulations. And we found it in two distinct cases with respect to the pseudo-momentum. So one is the symmetric case, when I have on average the same amount of right-going and left-going waves, and also in the case where the pseudo-momentum is concentrated on one of the branches, so mainly, for example, right-going waves. So this is, for example, can be a relevant scenario around the Hawaiian Ridge, where I have mainly waves going to one direction. And how relevant is the inverse energy cascade that we see in the approximate solution, how relevant it is for the two-dimensional Bussinesky in long times, it remains an open question. Thank you.
Thank you, Michal. Very nice talk.
The constant C0, does it depend on the large scale and the boundary condition you put on the large scale?
Yeah, good question. It depends on it. It's diverging, and it's logarithmically diverging. And we're fine with that because we have another example in the Schrodinger equation, two-dimensional Schrodinger equation in the inverse energy cascade. The solution gives a diverging flux, logarithmically diverging, but it's exactly at the point where the dispersion relation vanishes at zero. For the Schrodinger equation, it's k to the squared, so this is one point where they vanish, and the flux is logarithmically diverging, but it's relevant. This is what you see in experiments.
So if you, in this case where you concentrate the pseudo-momentum in one direction, does that generate a flow? And
A mean flow?
Yeah, mean flow, exactly. And then how does that modify the story?
So I think it will greatly modify the story. If I would not have this mean flow, I would say I must observe an inverse energy cascade.
Right.
And the reason I'm so hesitant about saying that is because I think that this mean flow will really change the situation.
I mean, probably instead of the cascade, the energies go into the mean flow.
Yes.
Again, as the condensate. Okay.
That's in the cascade. Well, it's a direct drive into a mean flow.
Yeah.
Yeah, Moritz.
So can you leverage this procedure to other systems? I presume you can, where you break rotational invariants. Like, for instance, you have a strong magnetic field, and you could think of other as in non-sign-definite invariants. Does that work?
Yeah, so I think I can generalize it to equations that have a similar structure to the Bussinesky equation. And I found also the scaling in general dimension for a general system. The thing that I need to have is that I need the interaction coefficient to be homogeneous with respect to scale. And this is very natural for physical systems, because if the partial differential equations has only derivatives with respect to space, it will be homogeneous. And so yes, that works, for example, for Rossby waves in plasmas or in the ocean, and for rotating turbulence. And maybe there are examples that I'm not aware of.
Yeah, please.
When you were talking about the inverse energy cascade, what I thought you had in mind was the problem where you have a wave packet, the pseudo-momentum being localized actually excites long waves. And I was wondering if that's what you had in mind when you're talking about an inverse energy cascade, going from a localized packet to the Eulerian response, creating a large wave.
Yeah, I if I would think about this, then I will localize a packet. I will take it to be in small scales, localized in small scales, and if I have an inverse energy cascade, I expect it to go into larger scales, and it will also spread. Yes. If this is what you yes.
Can you say something about the separability that you impose? Does it, like, if I'm thinking about the flux, if I average over theta, it's local in K after averaging over theta, right?
I will get a homogeneous, so I do not impose separability. What I impose is that my function is symmetric with respect to dilation, or homogeneous in scale. And because it's one variable, so all homogeneous functions in one variable, they are determined on the unit sphere. And then your solution has to be separable. So I do not impose separability. I impose scale invariant or homogeneity or symmetry with respect to dilation. And then yes, if you integrate over the angle, you will have a flux which has this power, k. It has the form k to the -3. And not the flux, sorry, this is the solution. And it will give you a constant flux in the radial direction. On average, it's constant.
Same.
Thank you very much. Very impressive and interesting talk. I have a question about the link to geophysical fluid dynamics. So in 2D Bushnell system, your mean flow is restricted to A equal to 0. But in 3D Bushnell system, for every wave number, you have like a zero mode field. Don't you think in 3D dynamics,
You have, sorry.
so you have geostrophic mode at every single K?
For every single kx?
Yes.
Okay, yeah.
So don't you think mean flow wave interactions will take over in 3D dynamics in a different way?
I'm sure it will take over, as we see in experiments. But we see, so in the ocean, there is a phenomenological spectrum. It's called the Garrett-Mann spectrum. It has places where it's clearly not wave turbulence, but it has a tail at the end, which it really looks like a power law. It looks like wave turbulence. So it's a question where actually wave turbulence can be relevant in 3 dimensions for particular scales. And it's still an open question. But I think, yes, the mean flow in 3 dimensions, this is why maybe the reason the problem in 3 dimensions was not solved yet. It's much more complicated.
Okay, any more for any more? Okay, thank all our speakers again.